Let us start.
Let's.
Okay. Section 2 today. The speaker Anatoly Petravchuk, title Centralizers of Elements in Lie Algebras of Vector Fields. Please.
Thank you. Good afternoon to all. I will talk about Lie algebras of polynomial vector fields. That is vector fields with polynomial coefficients over arbitrary fields of characteristic 0. And the talk is based on results obtained jointly with Evgen Chapovsky and Daniel Yefimov. And now let K be an algebraically closed field or characteristic 0. One can assume that K equals C, the field of complex numbers. A, the polynomial ring in n variables, and R, the rational functions in n variables. Recall that a K linear mapping D from A to A that satisfies the identity D of Fg equals D of Fg plus F dg, Leibniz rule, is called a K derivation on A. The set of all K derivations on A is a Lie algebra. It will denote by W and of K. Note that each derivation on A is a polynomial ring, can be extended uniquely to a derivation of R, fraction field of A. The set of all derivations on R will be denoted by double n of K tilde. In the case K equals C, these Lie algebras can be regarded as Lie algebras of vector fields on the manifold C to N with polynomial or rational coefficients respectively. Recall that every derivation D on the polynomial ring can be written in coordinate form as a sum of partial derivations with polynomial coefficients Fi in A. These polynomials are images of independent variables xi. The Lie algebra W of K, consisting of all such derivations with polynomial coefficients, was studied by many authors, and structure of its finite dimensional subalgebras was described by Sophus Lie in cases n equals 1 and equals 2. In fact, Sophus Lie studied vector fields with analytical coefficients. And note that in the case n equals c, the problem of classifying finite dimensional subalgebras is open. For n is greater or equal 4, this problem is wild in the sense of representation theory, because it contains the hopeless problem of classifying pairs of matrices, square matrices of the same order up to similarity. This was proved recently by Vitaly Bondarenko and Anatoly Petravchuk. There are many papers and surveys devoted to the algebras of vector fields. See, for example, papers of Euler, Dreisma, Blattner, Babula, Grabowski, Gonzalez Lopez, Koriyama, Billig, Futori, Post, and others. We study centralizers of elements in the Lie algebra W of K. Recall that for a given element X in L, the set centralizers of X in L, this is the set of all Y elements Y in L, such that XY square brackets equals 0. Centralizer is the set of all elements that commute with the element X. It's called centralizers of the element. The structure of centralizers of elements is very important from many points of view. I only point out in a theory of Lie algebra centralizers of elements. In a Lie algebra, I'll give essential information about the algebra L. Of differential equations, every derivation D with polynomial coefficients determines an autonomous system ordinary differential equations of the form with polynomial coefficients. And if we know some derivations that commute with D, then one can simplify, in some cases, the system of such differential equations. And every derivation D determines a subfield kernel of the set of all rational functions from R, such D of F divided by G equals 0. These elements are called constants, the field of constants of D in the field of rational functions. This field is algebraically closed subfield of the field R. Our aim is to study the structure of the centralizer C in W and of K of D in cases if transcendent degree of kernel D is not greater than 1. One can say that in general the problem of classifying centralizers of elements is hopeless because in cases n greater or equal 4, one can deduce this from general situation. In order to describe such centralizers, we need some definitions. Let P and Q in a polynomial ring in n variables be algebraically independent irreducible polynomials. We will call a polynomial f from this polynomial ring PQ free if it is not divisible by any homogeneous polynomial in PQ of positive degree. One can write every polynomial G in n variables in the form G0 dot G1, where G0 is a PQ-free polynomial and G1 is a homogeneous polynomial in two variables of P and Q. The total degree of the polynomial H will be called PQ degree of G and will be denoted by such a symbol. Let D be a derivation on the polynomial ring A such that kernel of D in R, R is the field of rational functions, is of transcendence degree not greater than 1 over K. Then either kernel of D equals the field K, the same field, or kernel of D equals K of P, the field generated by K and the polynomial P for some irreducible polynomial P, or in another case, kernel of D equals K of P divided by Q for some algebraically independent irreducible polynomials P and Q. In the last case, the kernel of D in the field of rational functions does not contain any non-constant polynomial. And the next part centralizes in the Lie algebra of all derivations of the polynomial field in field of rational functions in n variables. And this is a technical lemma. Let D in W n of K minus 0, D is non-zero derivation with polynomial coefficients, and F the field of constants of D1 in the polynomial field K in the field of rational functions K of x1, xn. Then the centralizers C of the derivation D can be presented as C equals F D1 plus F dk for some linearly independent derivations D1 dk for some K between M1 and between 1 and n. And a corollary from this lemma. Under the conditions of lemma 1, if the field of constants of the derivation D equals K, the ground field, and then centralizers is a k-dimensional Lie algebra over the field K. And this situation is very simple, and there are examples of such derivations for any k from 1 to n. An example, consider a linear derivation. Let d be the sum of partial derivations with polynomial coefficients, and this polynomial are linear forms with aij constant from the field A, and let a Jordan normal form for the matrix aij be of such a form, a diagonal form, where lambda I are linearly independent over the z ring of integers, eigenvalues of aij. Then the centralizers has rank n over the field of rational functions and dimension n over k. Centralizers in the Lie algebra, the structure of such centralizers. Let d in wn tilde be a derivation of the field of rational functions for which the kernel of d, f kernel of d, has transcendence degree 1 over k. This centralizers is a subalgebra of this Lie algebra wn of k tilde of rank k over r, and this centralizers is the sum of such a form for some derivations d1, dk, which commute with the derivation d. Moreover, either C is a Lie algebra over f of dimension k. This is a very simple case, or it contains an ideal of rank 1 over R, which is a Lie algebra over f of dimension k minus 1. And now centralizers in the polynomial, with polynomial coefficients, in the Lie algebra of all derivations with polynomial coefficients. This is the main part of my talk, because these results are here preliminary in some case, in some sense. And this theorem, the first theorem, let D be a derivation of the ring kx1 xn such that its kernel f in the field of rational functions is of the form f equals k of p for some irreducible polynomial p. We know that this kernel is generated either of a polynomial, an irreducible polynomial, or by rational functions p divided by q, for p and q algebraically independent over the field k. And this is the first case of the form k of p for some irreducible polynomial. And C is a centralizer of the element G in the Lie algebra Wn of k. Then if rank C over R equals 1, then C is of simple structure. C is monogenic Lie algebra k of p d0 for some p-free derivation d0 such that d equals f of p multiple d0, and f of t is a polynomial in variable t. If rank C over R is greater or equal to, then C, the centralizer, is either a Lie algebra of rank k over the ring k of p, or contains an ideal I of rank k minus 1, that is a Lie algebra over kp, and C is a sum of the ideal I and the one generated subalgebra k of pi t for some derivation t in C. This is the case when the centralizers, when the kernel contains a polynomial, a non-constant polynomial. Then it contains always an irreducible polynomial p, and this is the first case. And the second case, when the kernel doesn't contain any polynomials, non-constant polynomials. And the next theorem, let D1 be a derivation of the ring Kx1 such that its kernel F in the field of rational function is of transcendence degree 1 over K and doesn't contain any polynomial of positive degree. Then F equals K of P divided by Q for some irreducible algebraically independent polynomials P and Q in the polynomial ring. The derivation D can be represented as H dot F of Q D0 for some homogeneous in PQ polynomial F and PQ free polynomial H and irreducible derivation D0. Then its centralizers D of the element D1 in Wn is finite dimensional over K. This is not obvious, absolutely not obvious. This centralizers should be finite dimensional over K and is one of the algebras. C is K of PQM D0, where PQM is the linear space of homogeneous in PQ polynomials of degree M. In particular, dimension of C equals M plus 1. And second case, C equals K of P divided by Q D1 plus and so on PQ K of PQ D K intersection with W and K for some elements D2 dk which are linearly independent of the field R. One can give an estimation from dimension of C in terms of PQ degrees of minors of matrices consisting of elements which are coefficients of derivation D2 dk in standard base consisting of partial derivations. And example, we can consider the simple derivations D of the form here on the display. This derivation is simpler that is D has no invariant ideals in the polynomial rings besides zero ideal and the same ring. For this simple derivation, the centralizers of D is very small. It contains derivations of the form KD, where D is derivation D and K are constants. One can also formulate a result about linear derivations. Let D be linear derivations is a matrix AIG and lambda 1, lambda n distinct eigenvalues of the matrix AIG. If lambda 1, lambda n are linearly independent over Q, Q is the field of rational functions, then the centralizers of D in Wn consist only of linear derivations. Thank you for attention.
Thank you very much for talking, Professor Anatoly Petrovsky.